Okay, welcome everyone to the monthly colloquium. It's a great pleasure to have Professor E.D. Jemmis from the Indian Institute of Science give us this month's talk. Professor Jemmis did his bachelor's degree from the University of Calicut and then a master's degree from the Indian Institute of Technology in Kanpur. He got his PhD from Princeton in 1978. Following which he did a postdoc in Cornell and subsequently spent, I believe, 25 years in the University of Hyderabad. And then he moved to the Indian Institute of Science, where he's been there since 2005. He's won innumerable awards, is a member of many academies. If I take the time to mention all of them, we will lose more time. So I'll just like to say that he works in the broad area of theoretical chemistry, chemistry of boron and boron equivalents of graphene, which hopefully he may get to. So with that, I'd like to invite Professor Jemmis to give the talk. Thank you so much.
Thank you. Thank you very much. It's a pleasure to be here. I know several of the senior faculty here, and it's a pleasant experience to drive into the campus. Everything seems to be in its place, and that's not very common even in IISc. So this is nice. I went through the annual report of 2021 of the institute, and I realized that I don't really see any common points of research that is there. So I will try to say some things which are like a story, and you treat it as a story and nothing more. I will make it as accessible to a +2 student who have not taken chemistry after +2. So let's see how it is. So I would have a lengthy introduction, and I mean somewhat lengthy. Then get to a problem that has been very difficult for me to understand of a 3D allotrope of boron, and then get to a 2D allotrope which is just evolving from the point of view of experimental work. Computationally, it has been there for some time. Then this, unlike graphene, which will have a bilayer where the interactions are still weak, and you can think of the properties as a function of the angle between the two layers, bilayer of borophenes will have covalent bonds between them. And but then such a bilayer seems to be almost like graphene, monolayer. And there is something very interesting, if I get to it, that in graphene, if you want to increase the electron density, you have to dope it with a nitrogen. If you want to decrease it, you have to dope it with a boron. But if you want to have that with borophene, you only have to increase or decrease the number of hexagonal holes in this, and you will get to that, if at all. You could stack, of course, more of them, a bilayer, trilayer, tetralayer, and so on. And with each of these layers, you could have the equivalent of graphite, the borophyte. So you see the options are large. Now, I talk of it as a story. It started in my first year BSc. There was an excellent teacher who was talking about the relationship between methane and diamond, benzene and graphite. And at the end of the class, I happened to ask, is there something like this for boron? And we looked around, and there wasn't anything like this in boron at that time. You looked at books, looked at books and looked at journals. There was not really anything that one can get. So I went on to a master's, and I asked the same question in Kanpur in the first semester, and they said, well, not exactly known, but you should look at boron-related things. And so I started looking at boron-related things. I thought I will do something more, and I went to Princeton and I asked them, and then something else happened. And that something else is, you do this and you go there, and you actually do what your professor wants to do. And he said, well, what you are asking is not so very definite. So I don't know whether you can get, you are talking about something that is not written in a format of an operator and an observable, right? You say that, is there something like this in boron, right? I don't know. First of all, you finished your thesis. And you finish your thesis, the one thing about the thesis, in chemistry department at Princeton, at least, is that the thesis doesn't have to be defended. But, you have an examiner and a board of examination, and we didn't have to defend, and most of it is published. But along with the thesis, you have to give 3 research proposals, which are not connected with the thesis, which are not connected with your supervisor, and that you have to defend. The good thing about this is that these 3 research proposals are yours. You can go out and work on it later on. So I did work on something related to boron, obviously, but not reaching anywhere. In fact, that was my first paper from University of Hyderabad. I finished in 78. This is in 82. Now, but what did I ask? I only said, how about boron? In the carbon context, how about boron? And it took me 30 years after that 69 question to get the answer. So obviously, if I didn't do anything in that 30 years, I wouldn't even have a job. So I did other things. And while doing other things, you generate a philosophy of your own. That I decided that, I wouldn't ask just one question. I will ask questions and looking at periodic table questions on everything. So it became, general idea. Any question I would put it across to the elements, all of them. What I mean by that is, if I say CH bond activation, which is an important catalytic process, I would say, okay, if it is transition metals, I look at all the transition metals and see what is the best one, what are the ways of controlling it. If I look at hydrogen bond, I say, look, hydrogen bond, yes. How about other weak bonds? Halogen bond and sulfur bond and so on. All the main group element bond, maybe even transition metal bond of the weak interaction kind, right? Each of them will have its own conclusions. Look at gas phase chemistry of an element. Look at its own chemistry in the solution. Learn from these two and then design something for the solid with these elements. So it's essentially, of course, the last one is what I'm trying to get at. So my question was based on carbon and how about boron? And so let us begin from the beginning. And when chemists said, let us begin from the beginning, it is only hydrogen, not beyond, right? Not before. So there is hydrogen, there is H2 molecule, and you have a line H to indicate that there is a bond. Sometimes they write it like this, but it is implied that there is 2 orbitals and there is a bond, 2 electrons in this. There is an antibonding orbital that is vacant, or even a potential energy surface that we are talking about at this point of distance of the H2. This is the occupied orbital energy, and this is here. If it is this distance, maybe it is a little higher, this is a little lower. All that is implied by this drawing, right? But chemists are very approximate. You go to H3+, they still draw these 3 lines now. Earlier I said 1 line and 2 electrons, 1 bond, but here now they say, oh, it's a 3-center 2 electron bond, yet draw these 3 lines as well. So there is language of its own that is not so very well defined. I have a specific reason why I have drawn this as well. Of course, there is a molecular orbital corresponding to this 3s orbitals plus combination with 2 electrons, and then antibonding levels and so on. Now, carbon everybody seems to know because tetravalent and tetrahedral. I would not spend as much time, but we have this pattern. You go from methane to propane or ethane, propane, and so on. You drop these hydrogens. By the time you get cyclohexane, even the carbons are dropped. It is assumed that these are CH2s, but when it comes to here, it is a CH. You keep drawing, and of course, this is diamond. Totally covalent solid, right? You can do the same thing here. you take two sp2 hybrid or trivalent CH2 groups and then put ethylene. 3 of them get benzene and 2 of them together naphthalene. You draw it without the hydrogens, you get to naphthalene, and by the time you expand it, graphene, you don't even draw these 5 bonds, you leave it out, but it is all understood that way. Of course, you have graphite, and because it was easy for him to peel out a sheet, we have graphene. This is not quite true of borophene, because we don't have borophyte to peel out a borophene. That's a problem that we come to. And this is common now. You know that sp2 trivalent, slight strain, and you can make them all. Now, you can compare boron to carbon and say that, okay, wherever there is carbon, we can replace it by a B minus, right? 1 electron difference. If that is the way, of course, there is CH3 plus, we have BH3, CH4, we have BH4 minus. So there are lots of direct comparisons. Ethylene, we have B2H4 dianion, right? But if you want to make it neutral, you can protonate it, and if you protonate it, you get something like this, and this is what is there in +2 books, B2H6, bent bonds. We have the molecular orbital picture corresponding to it. This is what is there in books. Now, if you want to go beyond, okay, how about jumping from the 2D to 3D? We have 6 electrons, the delocalized 5 electrons, if you want to see. And of course, there is the erroneous thing in books, in all of the books, where they say that the CC bonds in benzene are equal because of pi delocalization. Nothing could be farther from truth. But all textbooks still have it, even today. Why, I do not know, but people are unwilling to change, despite the fact that they know that it is not the pi electrons that makes it equal. But anyway, if you remove 2 electrons, if you remove 2 electrons, we have a cation, dication, right? And that is a structure like this. They have made this pentagonal pyramid dication. There is even an X-ray structure that came out more recently. But, organic chemists treat this as organic. But if you make it neutral by replacing 2 carbons by 2 boron, we are removing the 2 charge, then that is C4B2H6. That's also known. That is somehow inorganic, even though it has more carbons. If you replace all of them, then you have B6H6 minus 4, electrostatically very bad. But you protonate it, you have B6H10. This is treated only as inorganic. So it's all the same, but this organic and inorganic divisions among chemists is so large. Now, why am I going through this? There is a attempt to get to boron by removing electrons from carbon, right? So if you remove 2 more electrons, we have C6H6 plus 4. That's of course not known. But if you replace 4 carbons by 4 borons, it becomes neutral. So this is C2B4H6, that is known. B6H6 minus 2, if you replace all of the carbons by boron, that's also known. So we have suddenly found that, just by removing electrons from benzene, you can get to polyhedral molecules. And there's a lot of chemistry that is interesting. But I will jump to say that, this is not as important. Yeah, I will jump to say that when you look at all of polyhedral borane chemistry, we have icosahedron, pentagonal bipyramid, many other structures, and going from 5 to 12. Now, this one, B12, H12, 2 minus, is the most stable one. Why is it most stable? That's a question of its own. I will have to spend 15 minutes, so I skip that question. I will just assume that that's the most stable one. But there is a very, very interesting geometrical reason along with overlap that tells you that in this case, this has to be the most stable one. Icosahedral, B12, and nothing else, none of these. Now, once we decide on that, then like benzene to graphite, graphite is the most stable allotrope of carbon. Benzene to graphite, you condense them together and you get the most stable allotrope. One would think that we can make that from B12, H12 2 minus, where each BH is replaced by another B12 and so on. It is not easy to do this because it has a problem of space filling, translational symmetry. All that creates trouble, and there are there are metal borides which comes close to it, but with lots of vacancies. I have not indicated the vacancies. This is a problem of its own that we are actually working on for some time, but we haven't understood it yet. So there are so many vacancies, and how to predict or at least explain why the vacancies are where they are. That is easier said than done. But here we have one allotrope which is there in textbooks, which works well in the sense that you have B12, remove all the hydrogens, we put 3 B12s together. These 3 corners where one BH is broken, another BH is broken. So we have 3 hybrid orbitals coming in. And remember the H3 plus. We need 3 orbitals and 2 electrons. So we have in this process 1 extra electron. We only need 2, right? But then it is said by, this is the situation. There are 3 orbitals coming in, and we need only 2 electrons. But if you now look at this, we have these 3 orbitals with 1 electron saved. So 1 by 3 electrons saved per boron atom, and there are 6 of these boron atoms on the outer side, which forms these 3 center 2 electron bonds as indicated here, right? What it means is that suddenly you have the 2 electrons that is needed in B12, H12, 2 minus without any charge, except these boron atoms here in this triangle and the one below, they are connected to other B12s above and below by 2 center 2 electron bonds, so that you don't add or subtract electrons. So this is alpha rhombohedral boron, easily explained, and it is there in textbooks. Only the simpler things come to textbook. Now, structure of beta rhombohedral boron allotrope is far more complex, and that's the one that has taken me a long time to understand the way I would like to say I understood. So it starts with the B12. Yeah.
So when you say that, earlier you were saying, so earlier you were saying this analogy with aromatic compounds and benzene and so on. In what sense is this true? Like, for example, do they, even before going to a solid and so on, can you like concatenate them?
Yes. See, for example, if you look at B12, H12, 2 minus, it is also aromatic by all the definitions that aromaticity group will tell you. Like a shift of hydrogen, chemical shift in NMR, or a nucleus independent chemical shift that they measure in the middle. There are lots of criteria. If you use any one of them, you will see that B12, H12, 2 minus is aromatic. And that is one reason why this is, it's of course the most stable of the boranes, but that's another added reason why this should be the beginning point.
And this also has, this kind of delocalized electrons, resonance, stabilization. All
yes. In fact, I didn't spend much time on the electronic structure or the reason for the so-called Wade's rule, n+1 skeletal electron pairs, why the 2 minus charge comes in. I had a drawing, I didn't discuss this. So I was just wondering whether it will take even longer time. Okay. Yes, there is definitely delocalization. Okay. Yeah.
And this this particular alpha rhombohedral structure that you're saying, so there is what is the lattice there? What is the lattice structure you said?
Yeah. Well, one can look at the solid state structure of this and see what is the translational symmetry based space group, and all of that can be easily obtained. It's there and it is exactly solvable. Okay. So the problem is treated as complete, so to speak. Unlike the next one. So this is simple enough to be put in textbooks. So I didn't spend much time.
Okay.
My attempt is to develop a model that will allow you to think about this, then to be able to give a quantitative result from our studies for each of them. It is done and it is possible. Now, here one begins with the B12, and ideally one should begin with each of these boron atoms connecting to a B12. Instead, half of a B12 is added. Now half of a B12 is a pentagonal pyramid, right? Half of a B12. And each of these boron atoms will have these pentagonal pyramids. I have indicated 6 more in this, 5 more, so that the total of 6. So just to make it familiar, there is 30 boron atoms here. How is it 30? 6 into, the 5-membered rings and an apex. So this is the pentagonal pyramid. So outermost layer, if you take, 6 5-membered rings are there, right? And just below this, you have 6 individual boron atoms. And right in the middle, we have a B12. So if I were to describe this, it is a B12, right, which is inside a B6, and that is inside another B30, right? B30 is the outer one. Now, if I add the remaining 6 pentagonal pyramids, it becomes a little complex, but suddenly it looks familiar if you didn't look at it carefully enough, right? Why is it familiar? It is like C60, right? It is like fullerene C60. And the outside is actually B60, right? Why is it B60? B60 has 12 5-membered rings, right? This also has 12 5-membered rings. Only 6 are shown here. The other 6 is from these 6 boron atoms sticking up and down, right? So this is one of the building units. What I am trying to do is to describe the structure of beta rhombohedral borons, idealized structure. It's not the real one, but an idealized structure. So you have this B60, which is, of course, keeping a B12 inside. That B12 is these individual boron atoms, which is at the apex of the 5-membered rings. And right at the middle, there is the initial B12, right? Now, the attempt, if B12 is the most stable one, the attempt will be to generate more of the B12s, right? One way of doing this will be if I put 2 of them together, one pentagonal pyramid here, another one coming from another of this B84, then we will have one more, right? Like here, right? I have put 2 of them and you have another icosahedron coming in. Now B84 is very large. You cannot bring 12 B84 around the B84. You can bring at the most 6. So when you finish this 6, then you still have another 6 pentagonal pyramids. So those pentagonal pyramids also would like to be a part of a B12, and the unit cell is of course 105. So we have more atoms. So what happens is it has a B10 unit of an unusual B10. This is a 5-membered ring. If you look at this. This also is a 5-membered ring, and the side here also a 5-membered ring, and the central atom in the middle. So each of these 5-membered rings is a part of a pentagonal pyramid, right? So if you put that on the top of a B84, we have one icosahedron coming in. We can put 2 more like this, right? If you do that, yes, there is a B84, another B84, a third B84. In the middle, we have a B10, right? Now, the unit cell has only 105 atoms. I am trying to describe the way it is organized, right? The way it is organized, one unit like this, this whole thing is connected to another one of the same kind through one boron atom, which means that this B10 or this larger unit, now it is 10. There is a pentagonal pyramid, another pentagonal pyramid, a third pentagonal pyramid. We have 18 of these plus the 10, right? So 28 of these atoms are connected to another 28 through one boron atom. And that, I will cut it out and show that's the only way it is possible, a side view. There is that one atom that connects these. I have added the hydrogens, trying to see what is the electronic structure of this from a separate calculation. If one were to describe the way it is developed, we have 105 atoms. Either we can say it is a B84 plus a B10 unit, that is this with another boron and a B10, or we can say how many B12 units are there. See, if you take strict B12 units, there are 4. Now, how does it come about? There is one inside this B12, and there are half B12s, because we have each of these B12s, half each of these B6 units becoming B12 when the 2 B84s come together. So we have 4 B12 units, and then B57. B57 is because this is B28, another B28 connected through this. So we have B28, B28, B57. This is our unit cell. Now, this is an idealized unit cell. The experiment doesn't give it in full. If it is B12, we know already that there are 4 B12, so we should have 8 charge. Right? B12, H12, 2 minus, 8 charge. This one, B8, B28, we don't know what is to anticipate, what is its electron requirement, right? And then we decided that we should do something like this. Benzene, naphthalene, anthracene, we have a rule. We decided that we should look for something that will take B12 into something that is condensed and so on, right? So we made a rule to, like Huckel rule. You can do this with computations and get the rule out, right? I'm just giving you the rule to see what would be the charge that is required for putting B12 together. When you put B12 together, you have a particular way of getting the charge. For example, this is a B12 connecting to another B12, sharing a phase. It could be sharing a 4-atom or an edge. There are many ways of sharing. And we could find out what would be the number of electrons required if this is true. And we found out that according to the rule that we have made, this will have a minus charge. This was 2001 and this was not known. So there was a little of a apprehension, but it took another 6 years before it was made. This is the structure. There is an anion. And we used this. Well, you can put a B12 together in many ways. All of that can be found just like benzenoid aromatics. We can apply this to all kinds of systems, and that was more interesting for the chemical world, that many things were explained by this rule. And once that happens, what happens is that suddenly, without the reason that we have looked for the rule to explain the structure of beta rhombohedral boron, textbooks took it up because it is available for applying to many other things, right? But they don't talk about beta rhombohedral boron, none of them, because that is too complex for them to put it in a textbook. But the rule is there. So we come back to this and say, what happens to this when we look at this rule? I didn't explain the rule because it is kind of trivial. M is number of polyhedra, N is the number of, N is number of actual vertices, O is the number of polyhedra connected through a single atom. But if you do this exercise, B57 at 36 should be a +3 charge species. It has extra electrons. Now, when we go back and check this, B12, H12, 2 minus, and we have B28, B28, this should be +3, this should be -8, right? Which essentially tells that B105, if it is to be electron sufficient, it should have -5 charge. But then an element has to be neutral, right? So there is something quite not right. And you can look at this by any kind of band structure. You find that, yes, it should be a metal if this is true. So obviously there is some problem. We had also done this and find that, yes, there has to be something wrong with this model. Now, the properties don't say that boron is a metal. Boron is not. Beta rhombohedral boron at the most is a semiconductor. So there is something wrong, and we try to go back and look at the X-ray structure once again. There was a refined X-ray structure that had come out in '88, and the more we read it, we find that there is a limitation even in the X-ray structure. They find that the only way they can improve their refinement to get some tally with what is observed is to add 1.66 extra boron atoms. Now, 1.66 extra boron atoms, 1.66 into 3. Each boron has 3 valence electrons, right? 1.66 into 3 is 5, right? So this 5 electrons that we are looking for is somehow obtained by adding electrons somewhere, by having extra occupancies of the boron. So B105 is actually B105 plus B1.66. B106.66 is the unit cell. We thought the problem is kind of solved. But then, we got the original diffraction pattern and looked at it again. Then one finds that this is not quite the same. if you look at the B57 part, somehow it has one atom missing. In the refinement, if one looks at it correctly, one atom is missing. And that was a little of a perplexing one. We wanted to see where would this atom be missing. This is the B57 unit, 28 and a center atom. So we looked at the molecular equivalent of it and found that the atom that is easiest to miss or least energetic would be one of these. There are 6 atoms here of these 3 and another triangle here. One of these would be the easiest to remove. And we looked at this. If it is 1 out of the 6 that is removed, that means only 5 out of the 6 is available. The occupancy percentage should have been 83.33. But the experiment shows that it's ranging 73 to 77. We looked at this experiment. What is this experiment? People make pure boron, melt it, and cool it slowly to get the crystal. Rate of cooling gives you different crystals each time. Now, we looked at 3 different experiments, and the difference between these experiments is that this is the one that is cooled as fast. This is the slower cooling, and this is the slowest. It looks as though from the melt, when one is getting the crystal, if you do it very slowly, atoms are organizing itself, so to speak, to have the vacancy and get to the structure. And one finds also that there is some extra occupancies that is around that is decreasing, right? So it looks as though, there is the attempt to get to the structure closely. In fact, very interesting is the experiment that is reported. The experimentalist had the, the courage to write that, courage to write that my boron is not pure. I have impurity in my boron, but the impurity is also boron. He has the idealized unit cell and then the gaps, and he has to put in some borons in places that are not related by translational symmetry to get the refinement correct. So, it's a very strange statement that I have impure boron, but the impurity is also boron from an idealized crystal point of view. Now, once we get this, we can easily see that we have B8, B28 plus 3. Now, this plus 3 charge will not be there if you remove 3 electrons by removing one boron. So, by having this vacancy, the crystal has removed the necessity for charge separation, right? So, the remaining one boron atom that is there is added on to the 1.66 that was already there. So, this is B2.66. Now, 2.66 into 3 is 8. So, these 8 electrons here that are required are obtained by this 2.66 electrons appearing in places which are not connected by translational symmetry. Now, you can see each experiment will lead to something else because these are extra occupancies that are coming in. And each time you make an experiment, you get into a different result. So, we have this picture here. B106.66, which is decent enough. Now, what do we do with it? You could, of course, try to check whether this is true. When I came to IAC in 2005, I thought I will really do a dynamics and find out which is the best structure for elemental boron, taking 10,000 atoms and doing the dynamics and finding out. And I realized quickly that it is impossible to do. Even at that time, we had a blue gene, they were willing to give me for a week. No, it doesn't help. Of late, using AI and ML, it is beginning. But even if I succeeded in getting a structure, it doesn't mean anything. It doesn't tell me why it is that way, right? So there is a difference between getting a structure and understanding it, and also to ask why the structure has turned out the way it is. So I am more interested in that question than actually getting an exact numerical answer. Now, this it tells so many things. It explains so many experiments that are already there. How did it, see, for example, LiB13 is reported. But when one looks back at the crystal structure very closely, you find that it is actually B10 for Li8, right? LiB13 is reported, but it is actually B10 for Li8, and Li8 is, the lithium plus is randomly somewhere, but 8 electrons are given, and that 8 electrons is what is required in this 104 atoms, B48, B56, right? So the B2.66 vanishes. Instead, 8 lithiums come. Hundreds of such structures are there in literature where people have made it for various reasons. I give another dramatic one. There was a series of boron, iron boride that is studied by weight ratio of iron and boron, systematically varying, just to see the properties and how it changes. And you find something very unusual. I have picked 3 points out of their, 2 points out of their data. And these 2 points correspond to the weight ratio that they had. Now, what is interesting is, from MOSBAR, they could see whether the Fe is in +2 or +3 oxidation state. Now, it is in +2 oxidation state if this was the weight ratio leading to this particular molecular configuration or molecular formula, which means that with +2 you can get 8 electrons. If it is Fe 2.66 equivalent, it has to be +3 so that you can get 8 electrons. But the B104 part remains the same, right? You can think of this way in many, many different ways. Let me get to, see, the earlier problem is not over in the sense that there are ways in which you can make changes.
You're telling us all these facts, all these structures. Can you just tell us how? Can you? Yeah, sorry. I would like to know how do you set up a calculation for such a complicated system? What are the methods you use to arrive at this? Because otherwise, this is just somebody telling me these are the pictures, this is the experiments. How do you do this quantum chemistry calculations?
Let us say first the structures are there. Let us assume the structures are there. I don't know why these structures are the way they are. I can calculate these structures and show that is what it is. What is obtained experimentally is what you will get if you optimize the structure by set density function theory. Even that doesn't tell us why the structure is the way it is. So my attempt is, after having done all these structures, I'm trying to understand why, for example, LiB13 suddenly appears like the larger framework I showed you, with one boron atom missing at the B57 unit. One boron atom is missing. That X-ray structure shows that it is missing. I tell you it is missing because it cannot be there, because if it is to be there, there has to be a +3 charge. So that is the understanding that I am bringing in. Computations, I don't want to trivialize computation. Computations anybody can do, because we have softwares where I can draw these structures. I can take the X-ray data and make it as an input, and then construct each one of them. Somebody who is a little more trained, it's instantly. Then I can use the smallest functional and do the computation if necessary, right? Or I can increase the nature of the functional in the density function theory calculation. Those are easily accessible and people can explain. Now, my concern is that stage I leave it to people who can do easily. I say easily again, because for each of them, I have gone through this exercise. Initially, it was difficult, but once one learns how to do computations, it is easy. what is not easy is to be able to understand why the structure at the end has come out the way it has, and why the energetics are the way it is, why the band structure or the band gap is the way it is. We can calculate. For the next one, you can calculate. And the third one. And most work is actually in doing that. And I would like to be away from it because there are lots of people who can do that. So I'm concentrating more on explanations, building up explanations. That's why I didn't give any detail of any computation that are done. Not because it cannot be done. Right? Now,
broadly, is it that the electrons are treated by density functional theory and the ions are classical superplastic?
no, this is the whole thing is, now being studied by density function theory alone. Not because that is a good theory. I don't like it because there is no systematic way in which one can improve density function theory calculations. If I had a chance, I would go back to standard wave function based methods where we know that you can systematically improve the computations. But the density function theory, there are some people who will guess what is the best functional to be used. But right now, because of the limitations of computation, we do this, right? So within that, yes, everything is included. There is no separate classical potential-based data brought in, right? So the next one I thought is, yeah.
Can I ask one more question about these defects and impurities and so on? So these various statements, do they change if I take these materials and put them under pressure? Like how sensitive are these bonds and so on to pressure?
Yes. In fact, there are lots of studies where they have taken boron, elemental boron, and studied under pressure. Depending on the extent of pressure, you can get structures that are very different. And you see it will also come in here, what is thought of as 2D structures. Apply pressure and slowly it starts going to the 3D structures. There are new allotropes that are available only under high pressure, right? There we can see why the high pressure does it. Again, I'm building explanations by saying that if I have a way of putting pressure, I could make not B12, but the pentagonal bipyramid as the most stable arrangement. So suddenly you can move from an icosahedron based structure to something which is not based on icosahedron but other polyhedra. There are lots of studies of that kind as well. Not lots, maybe 10 or 15 of this kind.
But is there even a rough understanding of what kind of possibilities are there and what amount of pressure roughly is required for the transition?
Yeah, I think it is just beginning. I would say in that context, boron solid chemistry is, is like what was the carbon chemistry in the 40s or 30s. We still have a long way to go. We don't even have standard allotropes already known, like the one that I would like to say now.
But are there at least the reproducible phase diagrams?
Phase diagrams are there without knowing the details of the structure. Yeah, the boron phase diagram is very complex because in many places we don't know what the structure is, and people try to take one or the other and try an explanation why the structure is the way it is. Because it is so complex, most people have just given up.
But it's at the stage where it is reproducible, like one can do it one lab and another lab.
The same. No, even in the same lab, reproducibility is a different term here. For example, we have this 2.66 statistically extra boron that is there. Each experiment gives a different result. Each experiment in the same temperature, same rate of cooling. From the melt you are getting the crystal. The rate of cooling decides where the extra 2.66 boron atoms are distributed. Computationally, people have tried to start with this B104 as a rigid part and then see what happens to the added boron. Let's take 106 only, right? Or 106 into 3, so 320, and see where those atoms go. Right? Even that, after dynamics for a long time, you get into different places. So reproducibility, that is why I said there is an inevitability of uncertainties. This will stay. But if you go to LiB13, uncertainty is gone. Of course, uncertainty is there where the Li plus is there, but the boron is safe.
Okay, so the statement is that if I take LiB13 and there's a standard way to crystallize it, and you get the same ratio stochastic,
except for Li positions, the Li plus positions.
Okay,
that varies still.
Mm-hmm. So the crystalline structure is still very variable.
That is reproducible. Yeah. The beta rhombohedral structure is reproducible for the larger framework of this, but for the 104 atoms, it is fine. The 2.66, that plays around.
Okay.
So it is inevitable. That's the nature of it. Unlike diamond, it's definite. There is no question. So in graphene, same thing happens. Sorry, in borophenes, same thing happens. In fact, worse. That's that's what I wanted to get to. Now, 2D allotropes. Let us assume that we replace each carbon by a B minus. Right. So we have graphene with B minus, and we have something similar. That is MgB2. For every 2 B minus, there is an Mg above. So MgB2 is having alternating Mg and so-called boron minus graphene layer. And we all know the properties of this. It was a sensation 20 years ago. Superconducting at 40 degree Kelvin, a binary solid, and all kinds of things was there for some time. But if you really look at this and say that, okay, I replaced the Mg by a boron, right? Then I have one plane. The Mg was different atom, but boron, everything is same, whether it came from the original boron or the new one. So you have triangulines, right? There is an additional atom in the middle of the 6-membered ring. There are only triangles now. People have studied this, and you find that this is not a minimum. It actually has a layer going up, a row going up, another row going down. It's a kind of striated structure. Many people have done this. In fact, we were beginning to study these things in 2006. We had reached some place in 2007, and I did something very, very foolish. Went away for 5 years. I didn't do anything for the next 5 years in this field. But strangely, a lot of computations came in the 5 years, but no explanation still. What I mean by this is the following. This is the binding energy per atom in terms of electron volt. This non-planar structure or striated structure is still more stable. If I remove some atoms here, right, in fact, it is even more stable. Some holes, and in fact, the best is if you remove every 9th boron atom, right? We had done this, many people had published this already in 2007. But why is it so? Why is the whole 1/9 whole density more stable? That explanation stayed on till, without an explanation for another 5 years. So when we got back, I decided to look at this again. And, we had B3, B6. I just took another stoichiometry, MgB2, Mg3B6, B3B6. Now, one thing that we notice is that if you replace an Mg by a boron, we are adding one extra electron. Right? Mg has 2 valence electrons, boron has 3 valence electrons. If you want to bring back to the graphene electronic structure, right, we need to remove 3 electrons if you have B6, B3, B6, right? 1 Mg, 1 electron extra, 3 Mg, 3 electron extra now, 3. So one way of removing 3 electrons will be to remove 1 boron atom. Now 1 boron atom means we have removed the 3 electrons. So we have come back to the graphene electron count, right? This graphene electron count is the 1/9 whole density that we talk about. That is, every 9th atom should be away, should not be there. Now, there are, of course, interesting consequences of this. Where will we remove the boron atom from? In other words, how will we organize the holes? Now, we can have an infinite way of organizing holes if you have the ability to make larger and larger unit cells, right? We can have many possibilities. The energy differences are not very large. So already you see the uncertainties coming in. Where will the holes be? But that's one level of uncertainty. Now, if we calculate this, this is the 1/9 hole density, that's the most stable one. If I were to take the relative energies in terms of milli-electron volt, if there is no hole density, it is higher in energy. 1/9 hole density, it is 0. If I increase the number of holes, then also it is worse. So there is some optimum hole density that is possible. Now, at this stage, it was still curiosity. People are doing computations. There is no experiment. But in the last 10 years, especially between the period of 2015-16 to 2020, a lot of experiments came. But what are these experiments? People have taken silver 111 surface and deposited boron atoms. And those boron atoms take positions that are the best if you can do it slow enough. And one finds that it has the structure of a borophene that we are predicting, except the hole density is even higher. Instead of 1/9, it is 1/5 or 1/6. And one can imagine that silver with a reasonably low work function will stabilize a borophene if it can accept electrons, right? And so there will be more holes than what is there in the 1/9, so that it requires electrons, and so we have this. We try to do this immediately on the metal surface. Now, these are computations. I am not giving the details. It took a long time. Now, we have taken a 111 silver sulfurs as 4 layers of silver. That's it, right? And then put this boron atoms and see which is the most stable one. And you find that
just one question about that. In these are essentially minimization.
Yes.
Right. So do you prescribe the energy and then find the optimal hole, or is it the other way?
It's the other way around.
Yeah.
Of course, only in limited cases we have done the dynamics, where we have kept even the top layer of silver free to move, and then the boron layer. But what one finds is that when you put it on the metal, larger hole density is required, as we anticipate. Now, this this gave us some confidence that there is some explanation that we can get. So questions were asked: if it is there, what is the way to get it out? To get it out, you have to give these electrons again. If you give it, if you give these electrons again, it can come out. This is a suggestion just made by us, not experiment. We think that controlled hydrogenation might allow people to lift this one layer out. But that's not what I wanted to talk about. I want to talk about bilayer now, which is very different.
Sorry, just experimentally, you said there is a higher hole density, but is the structure determinable?
Yes, what is done is you have the layer and you have a scanning tunneling electron microscope ready, and the tips move over to see what is the place of the hole. So each of them, that's the only characterization done.
Mm-hmm. And we also understand the bond strengths and so on, whether they're all the same.
Computationally, yes, they are not all the same. In fact, this this paper describes why it is not computationally, the bonds are not of the same kind, and where the hydrogen should go, or even a metal like Li, you have to seep in the metal, so to speak, so that one can get the layer out. Now, there are only 2-3 groups in the world doing it. in IISc, when I talk to all the experimentalists there, none of them have even heard borophene because it is recent and it's not easy to make it, right? So they are not worried about it, but they will with time because these things have to be streamlined, so to speak, to make it. So more interesting is the bilayer. Why? Is there a way to avoid having holes? And like if I take this zero hole density sheet where one layer is above, the other is below, and so on going up, it's like if this is above, then there is an sp hybrid orbital sticking out, so to speak. It's a hexagonal pyramid. If you have two of them, two layers like this, right, there are orbitals sticking to each other, and one could even make a bond. This is not unknown. Like if you have a carborane where there is a bond between two icosahedral boranes, this is already a pentagonal pyramid, another pentagonal pyramid forming a two-center two-electron bond. In the case of this bilayer, it's actually hexagonal pyramids forming the bond. Now, how does it help? 3 electrons are removed by removing one boron atom. Now, if I form one interlayer bond, it's a two-center two-electron, the classical localized bond. I removed one electron from the delocalized picture, right? If I have 3 such bonds, it is equivalent of removing one boron atom, right? So a bilayer of this kind, if you were to look at the band structure, interestingly, it is very similar to that of graphene, very unusual. The graphene band structure is similar to this. All the characteristics that you normally associate with the graphene is seen by the band structure of this one. Now, of course, this is just one possibility. There are many possibilities. The reason I say many possibilities is that we could have one bond, and if I were to take a sufficiently large unit cell, I could have some holes also, so that it is not necessary that I have 3 bonds per 9 boron atoms, right? I could have a mix of interlayer bonds and the holes. The possibility is endless. So it is inevitable that that is the way it is, unlike graphene, where it is all certain. But at the same time, we see that we could add or decrease electrons by number of holes. If I were to schematically represent bilayer like this, that is to say, for every 9 boron atoms, we have 3 bonds. I could think of a trilayer in the same fashion. Oh, this, we published this. There was no idea. People talked about it, but it was surprising. Last year, well, just at the end of 21, 2 experiments controlled deposition of boron atom on the same silver 111 surface. They could get a bilayer. Now, the bilayer, they have found, of course, interlayer bonds, but there is also a greater hole density because metal has to stabilize it. Right? So this is a very recent experiment. There is also a Chinese experiment which has come this year, January. Same, they have made it on copper, and there is the interlayer between this. So this is, when I say interlayer, it's actually BB bonds which are of covalent bond length. So hexagonal pyramids sticking out towards each other, and of course more number of bonds than, holes than what we anticipate. Can we go beyond multi-layer? If you have 3, what happens? You see that the middle layer, 0 hole density, let us assume. The middle layer with 0 hole density, there will be 3 bonds in this middle layer. So it is electron sufficient. But the top layer has only half of that because the other half goes to the other side. So we have a problem of extra electron density on the top and bottom layer. And so the top and bottom layer should have holes to compensate. And how many holes? For 18 electrons, for 18 boron atoms, if you have 1 hole, that is enough. So the hole density should be 1 by 18. So this is not very complex to understand. Of course, this is not known yet. But in 2018, bilayer was not known, right? Now bilayer is known. So I do feel that it's only a question of time. We have a trilayer, a tetralayer, a pentalayer. What is interesting is that with each of them, we could think of borophites, where you have outer wall stacking, right? That is easily said. When we look at it, you find that a van der Waals stacking of bilayer would have larger number of possibilities where it tries to form bonds, not of the regular two-center two-electron, but a B4 unit, a rhombohedral B4 unit connects. So the complexities are large, but the possibilities are there still. So, so my attempt is to tell that there is a model to think about it, right? Until a possibility that the bilayer could be thought about, there was no reason to look for it in the experiment. But once we say there is a model, then suddenly you see interlayer bonds and holes, and there is an interplay between them. It's just beginning. There are several ways in which one can anticipate this, developing. In 2008, when I was writing this article in Current Science, there was just the possibility. In 2022 in Current Science, I could say that, look, there are some already known. And the emphasis here that it is borophenes and borophytes versus graphene and graphite. Variety is infinite. Well, I think it's a question of time. Why boron? There are many reasons, and I think I will stop at this. I skipped this part of the connection of 2D and 3D, so I will stop at this stage and thank thanks for the invitation. First of all, it is nice to be able to come to a place where I don't understand anything of what you do and still talk about something. Of course, thanks again. I have a very benevolent department, which, after 6 years after retirement, is still keeping me there. And I have the good fortune of having good students who could be told some very vague things and they come up with interesting ideas. This is our new building, not so very aesthetically pleasing like the earlier one that we had. These are the main people contributed to this research over the years. Only Ringu Vane is of the current batch. This is just in front of the building, and I stop at this stage. Thank you for patient listening.
Are there any questions?
So in graphene, of course, like now people have started asking what happens if you kind of have multiple layers which are slightly misaligned and so on. But are there similar kind of statements?
People,
these layers?
Yeah, computationally people are looking at it, began to look. In fact, I wanted to study this, but my expertise in superconductivity is minimal. So I really would like to collaborate with somebody who understands this so that I can see. I have looked at the band structure of graphene, right? I have looked at the band structure of the bilayer borophene. They are similar. Now, if you were to put bilayer borophene on another bilayer borophene, what is the kind of dependence that we have as a function of angle? These are all questions that are being asked now. Experimentally, first they have to learn how to get these layers out. And that also is intentionally going on. Even, one paper came out this year, possibility of pulling it out. So the number of experimental groups working in this area is limited, maybe 5 or less. That is the issue. It is right now it is difficult experiments, but it will come through soon. This is my feeling.
Okay, just one more question. So when experimentally you try to make bilayers, so it's just done by deposition. So you have one layer deposited on silver, and then you try to deposit one more layer on that.
No, we don't have any control. The silver surface, and one is depositing boron atoms at different rates to get a monolayer or a bilayer. If the rate is slightly different, not as controlled, then you will have clusters on the surface. You will have even, B12 or similar clusters on the surface. It's not the atom deposition as in STEM. You pick one atom and put it there. No, it is the STEM is after the surface is deposited with a layer or two layers. So it is a controlled deposition that gave the second layer, not after making one layer and then getting.
So you get many clusters and then you choose, or like bilayers.
No, one has the metal surface and then one deposits, and depending on the nature of the deposition, you get a monolayer or a bilayer. And in silver, on gold, even if you do that, you don't get. So another attempt is made, that is, you have a set of clusters on the silver gold surface, melt the gold, so the boron goes in, and then slowly cool it to push it out. And that way they have got the monolayer. So different kinds of experiments are being tried.
Okay, thank you.
Hello. Yeah, I had a more basic question. Like, as we know, like in organic compounds, like carbon has affinity towards a lot of elements. Like it can form alcohols, it can form acetones and esters and whatnot. Is this story same for boron?
Except there is one set of chemistry that is imitating carbon, which meant that like BH4 minus, you can have tetra methyl boron minus, and there is that chemistry fully. That chemistry is very important. The organoboron chemistry has done many things, but there is the boron's own chemistry, like carborines, B12, H12, 2 minus, or C2B10. These are the ones that has its own chemistry, like ionic liquids. One of the anions that are commonly used now is CB11, H12 minus. It's an icosahedron. And people are trying hard to make C3, B9, H12 plus, which is not yet made, but people are trying hard. So there will be, one spherical cation, another spherical anion. In fact, we were looking at the dynamics of how to make this cation as well. So there's a lot of chemistry of boron kind of the boron itself, not connected with carbon. Right. So there are two different levels.
Yeah, that's true. My question was on the lines of like if boron is so similar to carbon, if you just add this electron, then observationally speaking, carbon seems to be somewhat special, because if you look around, all sorts of compounds have carbon in it, but boron is nowhere to be found.
That's right. You look at the periodic table as a whole of the main group part. Then you go from lithium to fluorine. See the variation in the bonding, right? Lithium 1 valence electron, beryllium, boron 3, carbon 4, nitrogen 5, but it has decreased, it is trivalent. Boron trivalent, carbon is tetravalent. So carbon has the natural advantage of making more bonds per atom compared to any other atom. So that is why nature has selected carbon for all of these, nature's game, so to speak. Is that kind of answer that you anticipate, or is there something else that you had?
Yeah, I was just wondering why boron is not so common if it's
similar. I think I teach third year UG students main group inorganic chemistry. So I look at this every year once as a different topic, so that it kind of evolves.
Okay, let's thank Professor Jemmis for a wonderful talk. Again.
Thank you.